Okay, so last hour we stopped here. First, we need to show that this is a well-defined operation. We know how to add vectors in our tree, but it's not clear that when I add two vectors from V, I will end up in V. Okay, if that is the case, then this will be an operation on V, so that V will be an abelian group under this operation. So we have to check that, and that's what I'm going to do. All right, so let's U and V in V. Okay, this means what? That U dot product with A is 0, and V dot product with N is 0, right? Because U and V are perpendicular to the vector A. A is this vector over here. Okay, so let's say U is this vector and V is this vector. They are, both of them are perpendicular to the vector A. Okay. Okay. So, well then, so U plus V dot product with A. Well, dot product by definition, by its definition, distributes over vector addition, and therefore this is just U dot A plus V dot A. But we know that this is 0. This is also 0. Sum of two vectors, 0 vectors, is just 0. Hence, U plus V is also 2. So, with this addition, inherited from our tree is an abelian group. Anlaşıldı mı bu? Şurada hani niye bu dağılma özelliği var diye sorarsanız hani doğrudan gösterebilirsiniz. You may just prove this identity easily. I mean, U is just vector U1, U2, U3. U is vector U1, U2, U3. You add them up, multiply by 8. You know how to multiply. You will get a sum. You can just decompose it this way. Okay. I will not do this. So let me say this part is exercise. Okay. But it's an exercise. So this is an abelian group. And then we have to do what? We have to check that the other two properties of being vector space should be satisfied. One of them was scalar multiplication. Right? This is the first property. First condition V should satisfy. V should be an abelian group. And then we should have a scalar multiplication. Meaning that whenever I have a scalar lambda and a vector in V, then I should have a way of multiplying these two. Well, we know that this is in R3, and I know how to multiply vectors in R3 by scalars. And what we are claiming is that V with the operations inherited from R3 is a vector space. So I will use the scalar multiplication of vectors in R3. So lambda times V is just, if V is just X, Y, Z, this is just lambda X, lambda Y, lambda Z. But we should make sure that, okay, this is also in V, right? Must check lambda times V is also in V. Yani Eğer bu vektör uzayıysa bunu skalerlerle çarptığında hala o vektör uzayın içinde olur. Başka bir uzaya gitmememiz. So we have to check this. What does this mean? Lambda times v is in v means it should be perpendicular to the vector a. So I should have this. But again, the properties of inner product is gives us the following. You can just take this constant outside, and what is this? Well, v is in v, therefore this vector is perpendicular to a. So this is just 0 times lambda times 0, which is 0. This means that hence the scalar multiplication of vectors in R3 gives a scalar multiplication is or inherits of elements of V by real numbers. I know how to multiply a vector in R3 by a real number, and we see that if that vector is in V, then lambda times that vector is also in V, so that this multiplication by scalars is induces a scalar multiplication on V. Yani range'deki vektörleri reel sayılarla çarpmayı biliyorum. O çarpım V'deki vektörleri de çarpıyor. Ondan kastettiğimiz nedir? V'deki vektörleri alıp gene V'deki vektörleri götürüyor. Yani çarpıp bir yere götürüyor zaten de. Önemli olan V'nin içinde kalması. Alright, so the third property that these operations are compatible, I don't need to prove that. Why is that? Because we already proved that when we were showing that R3 is a vector space, right? So since we already have proved that the operations are compatible, for the example R3, the restrictions of those operations to V are also compatible. Let me just explain this briefly. So, for example, we need to prove this, right? If U and V are vectors in V and lambda is a real number, then we should have what? Lambda times U plus V should be lambda times U plus lambda times V. But we prove this for all vectors in R3, right? So, and you know that V is a subset of R3, so U and V are also elements here. And if U and V are in R3 and lambda is the real number, we already proved this. Okay, that's why I don't need to prove this again. Okay. Anlaşıldı mı? Yani ufak bir sürü detay var. Onlar önemli. Hani pek de anlamadım. Çok önemli benzemiyor. Bir geçti. Tamam mı? Sizi bir yerde yakalarım. Genelde de sınavlarda olur. Yani küçük de olsa o detaylar anlamadan geçmeyin. Anlamıyorsanız hani üzerinde uğraşın, hala anlamıyorsanız sorun. Çünkü o detayı anlamazsanız o aslında fundamental bir şeyi kaçırıyorsunuz demek. Tamam mı? O yüzden o anlamadığınız şeyler sizin için bir aslında alarm. Tamam mı? Kötü bir şey değil. Hani dediğim gibi dünya kadar size information veriyorum. Hepsini bir anda anlamak, etmek, takip etmek zor bir şey. Ben de öğrenciliğimde yani bazı dersleri çok rahat anlardım. Bazılarında ise böyle hani sadece seyrederdim. Anlama işini evde yapmayı tercih ederdim. Kimi derslerde öyle olurdu. Hani o yüzden illa her şeyi burada anlamanız gerekmiyor. Ama neyi anlayıp neyi anlamadığınızı bilin. Anlamadıklarınızın da peşine düşün. Yoksa onlar peşinize düşer.
Dersler aynı mı hocam? Ne zaman peşinde?
Yani matematik yani size anlatılan matematik son 200 yıldır aynı. İşin tabii ki farklılıklar oluyor. Eskiden ders saatleri fazlaydı.
Niye azaldı hocam?
Efendim?
Niye azaldı?
Bilmiyorum. Yani daha eskiden zaten azmış. 12 Eylül sonrası öğrenciler derslerden kafalarını kaldıramasın diye arttırmışlar. Biz o döneme denk geldik. Her ders 6 saatte neredeyse. Yani düşünün 4 ders alıyorsanız zaten 24 saat ders var. Okay. This is supposed to be normal. Okay? But I admit that courses are usually just too fast. Okay. All right. Another example. So our third example. The set of all real value functions formed a vector space or R with the following operation. So V is the set of all real valued functions. I didn't tell you actually functions defined on which set, but let's just take, for example, the set R. So functions from R to R. Okay, X is a function. So this is my vector space. It will be my vector space. I have to tell you what are the addition operations, scalar multiplication operations. Yes.
Hocam şeyde bulmaz mıyız mesela? A'dan B'ye ama A ve B senin.
O sıkıntı olabilir. B'yi anlatsan your friend asked this. Why don't you do it more generally? And A and B are subsets of R. For example, 0, 1, right? But soon I will define my multiplication operation, and multiplication operation will be this. So lambda times f will be a function, another function, and its value at the point will be just lambda times that value. So if, let's say, for some x, this is just, I don't know, 0.5, okay, because it's a function to 0, 1, but let's say I choose my lambda to be 10, then 10 times 0.5 is just 5, which is out of this range. Therefore, this digit is no longer a function into the interval 0, 1. So that wouldn't work. Okay. This is simpler. This one would work. I could put arbitrary set here. That would work, no problem. But this one here would be better. Güzel soru. Var mı başka soru sonra? Okay, now let me just define what are these operations. So I have to tell you what the addition operation is, right? Whenever we are given two functions, how I will add them up. Suppose f and g are two functions. How we will add them up? This will be another function, right? F and g are functions from R to R. This will be another function from R to R. And how this is defined is the following. At any point, so I am now defining this function. This is a new function. A plus b of x is what? It is just f of x plus g of x. Here, this addition is the addition of vectors. In this case, just functions. This is the addition of two real numbers. These additions are different. Objectively. So this is true for all x numbers. So this is my definition of addition of two functions. And I have to tell you also how we multiply a function in this case. So let's do that. So, size vektör uzayı şudur diye söylenmesi lazım. Yoksa hani nereden bileceksiniz? Hani, milyon çeşit tanım yapılabilir. Her zaman ama böyle sınav odaklı şey yapmayın. Hani, siz de bir şey düşünüyorsunuz değil mi? Bundan nasıl soru çıkar? Evet, tabii bir yerde biz de düşünüyoruz. Bizim işin hoşuma giden çok hoşuma giden iki tarafı var. Biri sınav hazırlamak, diğeri sınav hazırlamak. Okay. What about scalar multiplication? So whenever I have a real number and a vector, which is a function, then I have to tell you how I multiply this together. So lambda times f is another function. So it's a function from R to R, and I have to tell you what the value of this function. Now I define you the value of this function. Lambda times x is just lambda times f of x. Okay, for all x in x. Here, this is multiplication of lambda with a function. And it is defined to be just lambda times the value of x under f. This is the multiplication of two real numbers. This is another thing, right? This is multiplication of a real number with a function. And the value of this new object, new function at this point is defined to be this gate. And that's definition. Okay, now, then we have to do what? We have to show that these operations are compatible. We must check that these operations are compatible. All right, let me start with the following. So let's say lambda is a real number. F and G are two functions. We have to prove what? We have to must show lambda times F plus G, right? This is the addition of two vectors, and then you multiply with lambda. This should be just lambda times F, and then lambda times G plus F. We have to prove this. How can you prove this? Well, this is a function. This is another function. I have to show that these two functions are the same. Two functions are the same if three conditions are satisfied. They should be defined on the same set. They should take values in the same set, and they should take the same value at each point. Well, of course, both of them are functions from R to R. This is how we define them, right? This is a function from R to R, and addition also like that. I have to just check that the value of this function at any point is the same as the value of this function at any point. So we just need to show that the two functions okay. Let me read this part. I am closely following the book, so if you miss something, you can just consult the book also. Show that the two functions agree at each x in R. So let's do that. Lambda times A plus G, this function evaluated at any point x. What is the value of this given? Well, this is lambda times a function. Lambda times a function at x is equal to what? This is by definition lambda times the value of this function at x. Yeah. Lambda times f, lambda times the function at the point x. By definition, lambda times that function evaluated at x. Yeah, early time. Here. And then here I use the first definition. F plus G at a point x. What is that? Well, that is just f of x plus g of x. Right? This is the addition operation of functions we define over there. And then we have what? Now this is a real number, this is another real number, and this is another real number. You know how to open this up. You know this from elementary school, right? This is just lambda times f of x plus lambda times g of x. And then what? Again, I use the definition of scalar multiplication of a function by a scalar. Lambda times f of x is nothing but the value of lambda times f, this function evaluated at x. And similarly, this is just lambda times g evaluated at the point x. Right? Bir fonksiyonu skalarla çarpmanın tanımı bu. O fonksiyonun değeri, fonksiyonun değerine lambda katıyla. And then this is just lambda times f plus lambda times g at x, right? This is the vector addition, right? Addition of two functions defined this way. So what we have seen is that this is true for each x. So this function at any point is equal to the value of this function at any point. Therefore, this function and this function must be the same. Okay? So this is true for all x, hence this function here, which is lambda times f plus g is equal to lambda f plus lambda g. Okay? Size exercise bırakayım, exercise. Similarly, so that lambda plus mu times f is equal to lambda f plus mu. It is similar, it doesn't have any new idea, but you have to go through all the steps for this gadget also. That was the second compatibility condition. And we have also the conditions multiplication by 0 and multiplication by 1, right? Let me just do one of them at least. So I have to prove also the following. 0 times f should be the 0 function. Here, this is the real number 0. This is the function 0. Right? İsterseniz bunu şöyle yazayım. Yani bu 0 ile bu 0 farklı. Şöyle yazayım. 0 bar is the 0 function. The additive, the identity element of the abelian group of functions under addition operation. Değil mi? Onu söylemedim tabii. This here, we said this is an abelian operation, but I didn't tell you what is the 0 element or identity element of this operation. What is the 0 function? 0 function, so 0 function, it is the function from R to R, and what it does, it takes any element to just 0. Okay, it is so the identity element of the abelian group of real valued functions is the 0 function. Yani bir sürü detay yazıyorum ama bir sürüsünü de atlamışım, görüyorsunuz. Well, let's see whether this is true. 0 times a function is the 0 function. Okay, this 0 and this 0 are not the same. Let's see. How can I check two functions are equal? Well, I have to just compute both of them at x and see that the result is the same. Now 0 times f at any point x. Now what is this? This is by definition just 0 times f of x. This is the product of real numbers. This is a real number, this is a real number. Well, 0 times any real number is just 0. But we know that this is nothing but the value of this function, right? This function takes the 0 value at any point. So what we see is that this is true for all x naught. So this function and this function are the same. Hence, 0 times f is just the 0 function. Okay. Similarly, similarly, 1 times f is just f. Okay, 1 times f. I mean, this function f is multiplied with the scalar 1, and the result is just 1. This is, of course, obvious because by definition, the value of this function is just 1 times f of x. But these are real numbers, so this is just f of x. So 1 times f at x is just f of x. Therefore, this is true for all x in R. Hence, 1 times f is just, okay. Sure. Yes, I mean, since it's an abelian group, in an abelian group or in a group, there is an identity element, and in any group, that identity element is unique. There is only one identity element. Yani sorduğu sorunun cevabı evet, ama o çok daha genel bir şeyden. Herhangi bir grupta bir tane identity elemanı olabilir çünkü. Değil mi? Neden? Why is that? In any group, right? There can be only one identity element. Why is that? Because if there are two, let's say E and E prime, two identity elements, then you can go like this. E is equal to E times E prime, because E prime is an identity element. But then E is also identity element, so this is equal to E prime.
Not to show that V is equal, right?
V what?
Is equal.
Well, actually, we have two, but you know, I just give up. Yeah. Sorarsam gösterin diye o zaman bekleyeceğim. Okay. Ne? Nasıl grup oldun? Benim grup oldum. Evet, evet. Okay. Okay. Let's say the expression lambda 1 times x, sorry, plus lambda 2 times y, where x, y are formal symbols, and lambda 1, lambda 2 are real numbers. To say that there are lambda 1 liters of oil, sorry, water, and lambda 2 liters of oil. Yani bir işletme demeyelim. İşte to say that in some place in a store if there are lambda 1 liters of water and lambda 2 liters of oil, then we express it using these symbols. So let be the following set. Okay, formal expressions of this type. So lambda 1 times x plus lambda 2 times y, where lambda 1 and lambda 2 are real numbers. Okay. These are just formal expressions. But it is a meaning, right? It is a meaning in this, as I wrote here. Now I have to tell you if this is going to be a vector space. I have to tell you what are the operations. First of all, B should be an abelian group. Okay. The addition operation, operation on B is defined as follows. Şey değiştirmemişim. Okay, so just go over this. So for the example, we consider the following type expressions: a real number times x plus another real number times y, which will mean that in a store there are lambda 1 liters of water and lambda 2 liters of oil. We define V to be this set of formal expressions, and now I will define an additional operation which will make this an abelian group. Now let's do that. Yeah.
Looks like it's R squared.
Sorry? No, just R. Just set notation. All right, so okay, how do we define? So addition operation will be an operation on B. So if I take two elements like this, let's say lambda 1 x plus lambda 2 y plus mu 1 x plus mu 2 y. Now I will tell you what this is. Okay, I will define this here. And the way we define it this way, take the coefficients of x, add them up. Take the coefficients of y, add them up, and you get a third element of the set B. Okay, so this is how I define two formal expressions. Ne iddia ediyorum? We claim that this is an abelian. So we claim V with this operation is an abelian group. Okay. For this to be a abelian group, it should satisfy the following conditions. It should be commutative, it should be associative, it should have an identity element, right? And inverse element also. I will not do all this in detail, but just mesela şeye bakalım. Associativity. Associated means what? If I take three elements, right? A and take group operation of the first two, and then take the group operation of the next, third one in this order, or right? Associated with this. So it means you don't really need parentheses. You may put parentheses wherever you like. Now let's see how we can show that this operation is associated. Well, we must proceed as follows. Let's say, let's take three elements: lambda 1 x, lambda 2 y, added to mu1 x plus mu2 y. I add this two, and then third element is this one. Let's say epsilon 1 x plus epsilon 2 y. Okay. Well, what is this? Well, by definition here, this summation is just lambda 1 times mu1 x plus lambda 2 times mu2 y, right? Added to epsilon 1 x plus epsilon 2 y. Now I have two vectors again. We need to add them up. How do we add them up? Well, we add them up. Just we add the coefficient. So lambda 1 plus mu1 plus epsilon 1 times x plus the coefficient of y here, lambda 2 plus mu2 plus epsilon 2 times y. Okay. Now, what I will do next, these are now real numbers. Lambda 1, mu1, epsilon 1, real numbers. And real numbers with respect to addition is an associate is a group, therefore this addition operation is associated. Therefore, this is just lambda 1 plus mu1 plus epsilon 1. So namely, okay, so that's good. Okay, let me change the board. Okay, so that's equal to the following. I can write it this way: lambda 1 plus mu1 plus epsilon 1 times x plus similarly lambda 2 plus mu2 plus epsilon 2 times y. Because the addition operation on real numbers is associated. And then we do what? Here the addition. So I can write it this way. This is just lambda 1 times x plus lambda 2 times y plus mu1 plus epsilon 1 times x plus mu2 plus epsilon 2 y. And lambda 1 lambda 2 y plus, now here's again I am using the definition of addition, so this is just mu1 times x plus mu2 times y plus epsilon 1 times x plus epsilon 2 times y. So what we have seen is that addition operation is associated, right? Here first I take the sum of the first two and with the third one, and that is equal to the sum of the first one with the sum of the second and third one. Değil mi? Önce ikisini toplayıp üçüncüyle toplamak, son ikisini toplayıp ilkiyle toplamaktan aynı şey. Dolayısıyla da parantezleri nereye koyduğumuzun bir önemi yok. Evet, süre bitmiş. Okay, next time I'll finish this example and then we will continue.